we're good.
Thanks. Did you get those loaded by the way?
Yeah.
They did come out? Let's see how that. Oh, this is only 4 gigabytes. Yours is 16? Oh, we're gonna be good to go then. I won't have to keep unloading.
64 gigabytes too.
That should. Whoa.
Whoa, mind blown.
All right, I guess I know what I'm asking for Christmas. I should have gone. I actually did go out to the Black Friday. I almost never do this. I don't want to go anywhere near the stores or go shopping. But I actually went out at 1 o'clock in the morning. I went to Best Buy. The biggest mistake I made all Thanksgiving break. With like 5,000 people in the store. But anyway, I should have picked one of those up, 16 gigabyte card. So anyway, there's still time. It's still the holiday season. So I'll work on it. Okay, so we combined this into a single matrix. That's the first thing we did. And now, what do we do next? Now we're ready to do the transformation. So I'm going to get 2 components here and set myself up for 2 slots. It's just the upper left minus upper right minus 3 times lower left. So upper left is a plus x. Upper right, I have to subtract b and subtract y. And then minus 3 times the lower left corner, so minus 3c minus 3z. Takes a little bit of room to fit that all in there. All right? And then, can somebody tell me what I'm going to get on the second slot? I'm ready.
2b plus
2b, sorry?
plus 2y
Okay. 2b plus 2y
plus d
Plus D plus
plus
W.
d
plus w.
plus w. That look good to everybody? Okay, does anybody know what I need to do next?
We need.
Separate it out, and how do I want to separate it out?
But you want to put all the variables for one matrix on one side, and then plus the variables of the other matrix.
I kind of want to get the 2 matrices separated is what you're trying to say. And that's absolutely right. Let's say for some reason you're stuck. You're not sure how to simplify this. There's just so many terms, I don't know what to do, right? What would you do if you're stuck?
Write the final.
Work backwards, right? You say, oh, down at the bottom, I want to have t of a, b, c, d added to t of x, y, z, w. I've got separated pieces, and then I can work backwards, you see. So if I work backwards, right, the line above this should just be a minus b minus 3c, comma, 2b plus d, and then plus, what is it, x minus y minus 3z, and 2y plus w. And does that work? Well, that actually is exactly what you were trying to do. You're trying to get all of the a, b, c, d's together, and all of the x, y, z, w's together. And this is the key step where you actually do that. Does that make sense?
So we always use that part so we can just say that we're going to take it back and like work from it. You know, like the second step is always taking that part and putting it back in here, right?
You mean from the bottom?
The second, no, I mean like the second step
Okay.
right away is just going to this right here, right?
I'm not sure I understand
Yeah,
what
yeah.
it
So
is.
the first matrix is that answer up here that we've been giving on the second step?
Yeah, second step,
Or
this,
third step.
this one?
Yeah.
Yeah, this is, right, this is just the answer of the transformation of the first matrix, and this is the answer of the transformation of the second matrix. Yeah.
But we can't jump to that right
Well, you have to be a little careful. I mean, if you work backwards and you get to here and you get to here and it's not obvious how to go between them, I might accuse you that you skipped too many steps. Right? So, if it's not obvious to me, my general rule of thumb is if it's not obvious to me, it's probably not obvious to anybody. Just kidding. If it's not obvious to me, I have to ask myself, could a person have did this in their head? Maybe. And if it's too much of a stretch, then I start getting nervous, right, about it. So, we good on that part? Let's check the scalar multiplication. I'm going to do it fairly quickly. By the way, I hope you guys understand there's absolutely no way I can review everything tonight, right, in one session. This is just intending to remind you of some of the different things we learned. But you're going to have to go back. If you're seeing this problem right now and saying, whoa, I feel shaky on linear transformations, that's your tip-off that you need to go back and review some linear transformation problems from chapter 5, right? I'm not going to be able to do 5 problems on this topic tonight, right? So this is just to sort of get your mind thinking about the material that you need to review, okay? That's why, in a way, it's good for having a review early. It gives you time to go back and figure out where you need to work on, okay? How do I want to start this part?
Would k be an element of all the real numbers?
Yeah, I need to take a real number k, so let k be an element of the real numbers, okay? And then what am I going to do?
State your,
I guess we didn't state the condition, did we? What is the condition for the, oops. What's the condition for t
T of
respect?
KB1 equals KTB1.
Say that again?
T of KB1 equals K of TB1.
Okay, good. So if it just says I can pull scalars out, right? Pull scalars out. Okay. All right, so we've got the condition, so we're going to start on the left side, right? So it's going to be T of K times the first matrix, A, B, C, D. Look good? And so what do I do first here?
Multiply it.
Yeah, before I transform it, I need to multiply my scalar k through the whole thing, right? So this is just going to be T of Ka, Kb, Kc, Kd. Like that. Okay? And what's next? Now I transform it. When I transform it, I'm going to get upper left minus upper right minus 3 times lower left, comma, 2 times upper right plus lower right. Good with that? Then what's next? Factor out the k, very good. So I factor out the k, and that leaves me with a minus b minus 3c, comma, 2b plus d. And I'm pretty much done, right? This is just, I factored the k out. I need just a little more room here. I factored the k out, so it's just k times t of a, b, c, d. Okay? Does that make some sense? Great. All right, I'm going to go over here if that's all right. Oh, you know what? I wanted to say one other thing about both of these last 2 problems that we did. On both of these 2 problems, the sets that we were working with and the transformations that we were given in terms of the entries of the matrix in this case, and over here again, the answer is in terms of the matrices, right? The specific entries, right? Sometimes you don't have to work so hard. So without going through a whole other example, I'll just remind you, let's go back to the subspace thing again real quick. If I gave you, say, 2 by 2 matrices A such that A is symmetric, this is not on the review sheet. I just wanted to remind you about that. And let's say I ask you to show that that is a subspace of M2 of R. Do you have to write out the entries A, B, C, D for the matrix for that? Does everybody remember what symmetric means, by the way? A transpose equals A. This is actually the condition for symmetric. My point is that if the condition for the set S is described in an abstract way, not with specific entries like this one was, then when I want to go to show that it's closed under addition and scalar multiplication, there's no need for me to write out entries of the matrix. I can just say, you know, let A and B be elements of S. Then A transpose, and you have this in your notes if you've been in class, because I think I did this exact example. But you just simply have to say A transpose equals A, B transpose equals B, and therefore A plus B, when I add them together, if I transpose it, because I'm checking if it's symmetric, well, we know that we can transpose first and then add, and so that you just do that. This would be the whole proof, right? This is the whole closure under addition for the case of, well, not quite the whole thing. Implies A plus B element of S. I would need that part. You don't have to make it so messy, right? After all, I could do something else if I didn't want you to play with the entries. I'll do that, right? Now, if you want to really do it with the entries, it's going to be really, really messy, right? With all the subscripts and stuff. So it's much better to just use this more abstract framework. Now, you cannot do that on this problem, because in this problem, the set S is itself described in terms of the entries. Right? There's no quick way of saying what this matrix is, or what properties it has. See the difference? Brandon, does that make sense?
Sorry, I wasn't.
See what I'm saying? Like a problem like this, right? Where and this is my set S, and I want to check closure under addition. You see, I have to do all this messy work. I have to show all these steps. I have to actually get my hands on each entry and add up each entry. But what I'm saying is that sometimes your set S, like in this example, is described more simply with just abstract notation. A transpose equals A. So when I'm checking that is closed under addition, you see my life is much simpler. I just leave everything abstract. And it's a short, easy explanation. Doesn't require as much, I mean, it's more abstract. I know some people don't like that. But it's also a lot shorter to write it out. Okay. I just wanted to make sure I made that point. I know I've made that point before, but it's been a few weeks. Sort of making it again. Everybody good with that? So my next question, I want to go back to the one-to-one onto both neither thing. And I want some help from you guys on how to decide whether it's onto or not. Does anybody have a suggestion for how to check that if that transformation is onto?
Find the range.
Find the range would be one way to do it. Because onto means that the range of t is equal to w, right? The range of t is equal to w. Can anybody remind me, how do I find the range of a linear transformation? The range, just by way of definition, the range is just a set of all achievable outputs. It's all outputs that can actually come out of t. Every possible output that you could get. So you're thinking like it is not necessarily this whole thing, right? If it is the whole thing, then the transformation is onto. But it might not be everything. The question is which outputs would have this form, right? So Sarah's got an idea for me. She said the word span. Span of what? Do you guys remember?
Isn't it T of V1?
Full space.
Okay, I hear people talking about row space, column space, and null space. All of those things are very relevant and important, but they only apply if you're talking about a transformation from Rn to Rm, right? If I'm having a transformation from Rn to Rm, okay, so side lecture here. If I have a transformation from Rn to Rm, a linear transformation, any such transformation can be written as some m by n matrix times x, right? And if I want to know what the kernel or the range is, the kernel of this transformation is just simply the null space of the matrix. And the range of the transformation is simply the column space of the matrix. Now, this is not something I was necessarily going to review a whole lot tonight. If I give you a matrix, one thing you definitely need to be able to do with it is find its null space, find its column space, find its row space, and find bases for any of those things. So if I have a transformation from Rn to Rm, then I could have found the range by taking the column space of the matrix. Do I have a transformation from Rn to Rm here? No. I'm using the M2 of R, right? So I'm not going to represent this transformation as a matrix. You actually can represent this transformation as a matrix, but that's Math 307. I'm not going to bother you with that right here, okay? So we don't want to go here right now on this problem. So I'm going to go back to my question again. Does anybody know how to find the range of a random transformation when it's not of this nice type?
Isn't it T of V1, T of V2, all the way to Vn?
That's right. You have to transform V1, V2, and so on up to Vn. Does anybody remember what are V1 and V2 and Vn? What are those vectors?
Those vectors.
Those ones?
I want I want to know. But what do they make up? What are they called?
W.
A basis. Yes, they are a basis for.
W. V.
You only got two choices.
W.
Well, I've written them as V1 and V2. They better be a basis for V, right? Okay, that's exactly right. These guys are a basis for V. So, now of course, any vector space has lots of different bases. You just have to pick one. But in the case of M2 of R, right, in the case of M2 of R, there's kind of a natural basis. I think I called it the standard basis. Can anybody remind me what the first vector is in the standard basis for the M2 of R?
1, 0,
1, say that again? 0, 0, 0. Yeah. Oh yeah, I mean another way to get the basis that I'm writing down is to just take this matrix and bust it apart into four vectors, and you're just going to get what I'm writing down here. Yeah, absolutely. So 1, 0, 0, 0. What's the next one?
T.
0, 1, 0, 0.
0, 1, 0, 0. Good. What's the next one?
0, 0, 1, 0.
0, 0, 1, 0. Good. And the last one?
0, 0, 0, 1.
Great. 0, 0, 0, 1. So we need to transform all of those. Okay, now let's go ahead and start doing that. For example, when I transform 1, 0, 0, 0, I'm going to put 1 for A. So you have to put the right numbers in the right places. 1 for A and 0 for everything else. What do I get on the output side?
1, 0.
A is 1 and everything else is 0, so it's 1 and 0, correct? Be sure to ask me, guys, if it's not clear what I'm doing, please ask me here. I'm simply transforming 4 specific matrices. Okay, so the next one is T of 0, 1, 0, 0. So if I put a 1 for B, what do I get?
Negative 1, 2.
Negative 1 and 2, right? And then when I put a 1 for C, I get negative 3 and 0. And when I put a 1 for D, I get
0, 1.
0 and 1, right? So what you're doing is you're going to take all possible linear combinations of those 4 vectors. What are you going to get when you take all possible linear combinations of those 4 vectors? If you collect them all up, that's what the span is. It's the collection of all possible linear combinations of those vectors. What do you end up with?
Basis.
Well, I mean, what do you actually get?
W.
All of W, don't you? Would you agree that every single vector in R2 can be written as a combination of these?
Yes.
Absolutely. I mean, actually, you don't even need this one or this one. You don't even need that, right? Even just the first one and the last one, that's already a basis for R2. So this does equal all of R2. Remember guys, the span is a set. It's a set of vectors that are spanned by these guys. So is this thing onto?
Yes.
Yep, the range of T is equal to all of W. So it is onto. All right, so now I've got an interesting question for you. Let's suppose that you don't like calculating the range of a transformation. It's just not your thing. It's not your thing. You don't like it, you don't remember it, whatever, for whatever reason. Would there be some other way to try and figure out if T was onto without calculating the range of the transformation? If we do the kernel, not the null space, stay away from this thing here, the kernel of the transformation. Because if I know, so why is that, John? Can you help me? Why is it that if I calculate the kernel of the transformation, it's going to help me figure out if the transformation is onto?
Because if the kernel is trivial, then the dimensions are equal.
All right, wait a minute. We already know that the kernel is not trivial, right? We already said it's not one-to-one.
Oh, I'm just saying.
Yeah.
In this case.
Yeah, there's a theorem, right, that relates the dimensions of these things.
So it's a formula too.
Yeah. Let's write that formula down. Let's write down the result here. We first learned this important formula in this context where we have a matrix. And the formula was that the rank of a matrix plus the nullity of a matrix adds up to, remember what it was? N is what I'm looking for. The number of columns of the matrix, right? So the rank is just the number of pivots. The nullity is the number of free variables or non-pivots. Every column either has a pivot or doesn't have a pivot, so there's n columns, so they have to add up to n. Very simple, right? For any matrix, this is true. The rank plus the nullity adds up to n, and you can always take your matrix and row reduce it, circle your pivots. That's basically going to tell you what the rank of the matrix is and what the nullity of the matrix is. But we later extended this theorem to these more general-looking transformations with the following thing. The dimension of the kernel of any transformation, which is, of course, the nullity in the case of this kind of transformation, plus the dimension of the range. Does anybody remember what it adds up to? The dimension of V, exactly. The dimension of V. What is the dimension of V in this case?
1.
We already said that, right? 4-dimensional here. So here's the point I think John was trying to make, is that if we can figure out this number, then through the back door of this formula, I can figure out the dimension of the range. So just for practice, let's try and figure out the kernel of this transformation. We don't need to, but let's just do it anyway. We already know that it's not one-to-one. But let's just try and find the kernel. All right? Does anybody remember how you find the kernel of a transformation?
Null space. Null space. Null space.
It's the null
Are you
space.
just... I don't want to go here, guys. It just gets over... seriously, a lot of people lost points on midterm number 2, is they kept going back to this thing. This is only in a very special case when you're talking about an M by N matrix. That's not what we have here, okay? So the follow-up question is, let's just say it this way. Find a basis for the kernel of T. So let me ask you again, how do you find the kernel of a transformation?
You just say that A, B, C, D belongs to the kernel if and only if this part is equal to zero?
If and only if the output is equal to 0, right? Remember that the kernel of a linear transformation is those vectors that get killed by the transformation. So the way I find the kernel of this transformation is I set this equal to the 0 vector. When you're finding the kernel, when you're trying to find it directly, brute force way, you just set the answer equal to 0 and try to solve backwards for which inputs would give me that 0. Okay, so let's do that here. So I'm going to set T of A, B, C, D equal to, in this case, it's 0, 0. And so that just means that A minus B minus 3C has to be 0, and 2B plus D has to be 0. Okay? Look okay so far? So really, it's this system that we're trying to work with. So what can I do? What would you recommend that I do with that system?
On the convergence.
Right, I need to build a matrix and find my free variables. This is like the first time I've been here for 2 hours. I haven't done one of these yet. It's pretty hard to believe, right? We've been doing this all semester, putting the vectors into a matrix. So the first row is what? 1, -1, -3. And notice there is a D variable, so I need to keep track of it, even though it doesn't show up on the first line. And then we're setting everything equal to 0 over on the right-hand side. And then what's the second row going to be?
0, 2, 0.
0, 2, 0, 1? Look good? Okay, that's basically in row echelon form. Oh, incidentally, by the way, I already know the dimension of the kernel, even though I haven't found it yet. What's the dimension of the kernel going to be? It's the number of free variables. I've got 2 columns that are free, which corresponds to C and D. Remember that these columns correspond to your variables in your system. So C and D are both free. So guys, the kernel is going to be 2. We got a 4 over here, right? So what's the dimension of the range? To make this equation work, it has to be 2. And 2 happens to be the full dimension of W. So, because W is equal to R squared. So, since W is equal to R squared, and the dimension of the range is 2, then the range must agree with W. In other words, it's on 2. So that's your backdoor method for figuring out if the function's onto without ever looking at the range. If you just know the formula, you can instead look at the kernel and then just through the back door find out the dimension of the range. I'm not promoting this, you need to be able to do everything. But it is kind of nice to know that there's more than one way to look at everything. As long as we've gone this far, we may as well go ahead and finish finding a basis for the kernel. So I have 2 free variables, right? So D is free. What do you want to call D?
T.
I could just call it D. I'm going to call it T, though. Yeah, you know, some of you have figured out you don't really need to shift the letters.
Yeah.
I like to do it, though, just because it really helps me remember when I see the R and the S and the T that I've got my free variables there. What is C going to be?
R.
You guys even know that I don't like S very well because it looks like a 5,
Yes.
right? So we use R and T. So then what is B?
Negative one half T.
-1/2 of T. And then I've got to go back and figure out what A is, which is going to be B plus 3C. Well, that would be -1/2 T plus 3R. Right? All right, so tell me how you like this. I'm going to give you my basis for the kernel of T. Basis for the kernel of T. I'm going to bust out the T. And I'm going to bust out the R. What do you think?